I will draw a picture. For RIP. It is very simple to perform routing calculations. I draw 3 devices here. There is a network segment behind this device. Suppose it is 3.3.3.3. The left device is R1. This is R2. This is R3. 3 devices. Then the RIP we mentioned earlier. It is the act of passing a vector. Data transfer and table addition. For example, now R3 has received a route here. Then it computes locally. After the calculation, a new table is generated. Then send this new table. R2 receives R3's table. Also start counting. Generate new table after. Then sent to R1. That is, for a protocol like RIP, it receives a route. First check whether this route can be calculated with itself and added to the local routing table. If the table is added, it will be sent out. So the algorithm it uses is actually receive first. After receiving the calculation, create a new table after calculation. Forward again. Then, for such a route, it will have a serious problem. For example, this route is passed to R3 here. R3 can only know who sent the data to it. Assume it is transmitted from the left interface of R4. Then when R3 goes to 3.3.3.3, it knows that the next hop is to find R4. Then R3 calculates locally. It passes information to R2. Then R2 goes to 3.3.3.3. It only knows that the next hop is to find R3. That is, for all devices along the way. They don't know where this 3.3.3.3 is. We call this behavior originating information that does not know a specific route. They only know about routing delivery. But I don't know the specific location of the route. This is a serious common problem of RIP itself. EIGRP is a bit more advanced. Then let's start talking about OSPF. What is link state? OSPF transfers not routes. Link state information. Link state information is not a route. A piece of data is sent out on behalf of the future generator. About 3.3.3.3. It is not passing the route about it, but a detail. For example, after R3 has a message about 3.3.3.3. This device will not immediately calculate and add tables. Please pay attention to my words. It received a routing message about 3.3.3.3. Will not be added immediately. If you add a table, it is a vector behavior. It will use this information. Generate a detail. Information generator. It is now received after. To tell the generator of other device information. It will put its own name on here called R3. R3 will tell other devices. The data they will receive in the future is given to them by R3. So now if this 3.3.3.3 is R3, it will tell other devices that there is a loopback address behind it. This is what it generates. Then after that, it will tell other devices about a link status of the information producer. There are actually 2 types of link states that are commonly used now. One is an Ethernet link, a point-to-point link. The Ethernet link was used on EIGRP just now. Point-to-point link. There are 2 other types. You will learn in NP stage. In the NA stage, just touch these 2 kinds. Okay. There is also a link overhead information. For example, the metric in OSPF is called cost. When R3 goes to tell other devices about 3.3.3.3, instead of directly telling them that they have a route to pass to them, then they add the table. Not like this. Instead R3 produces a detail. It will pass this detail to the pass to R2. Then when R2 receives this detailed content, it will be very different from the distance vector routing protocol. The first step is to flapping this information. The meaning of flapping is not the same as forwarding. Router-based forwarding is: received a data. Query the local routing table. Query next hop. Then forward it. It's called forwarding. Flapping refers to: it now receives a data from the right interface. Copy and send a copy from the interface on the left. This is called flapping. That is, in addition to the receiving port of this device, other interfaces if running OSPF, and also in the same region. Now a copy will be sent from other interfaces running this protocol. This is called flapping. So you will find it is not the same as RIP. RIP only needs to receive one data. Must be calculated locally. After finishing the calculation, give other equipment. OSPF is different. As long as it receives it, it will send a copy to other devices. Then calculate locally. Therefore, the propagation efficiency of OSPF is relatively high. First flapping and then calculation. This is the first step. Then for now, if the device finishes receiving locally, after flapping, the second step is to calculate the route. Only then will the calculation of the route be carried out. Then this calculation is calculated by the device itself. Please pay attention. It's not the same as RIP. In the future, when you reach the NP stage, you will learn the SPF algorithm. You will know about every node in OSPF. For example, this is R1. It will have a map of the topological information about the overall network. You can understand it as they will all have their own separate path. Go to all places on the whole network now. Everyone's picture is different. So they are actually calculated independently. Instead of like RIP. There is a global concept. And a concept without a global. The difference between them. We will not mention the specific algorithm at this stage. For now. Here are its two steps. First flapping and then calculation. This is what we call these two. So for the whole process now, everyone also needs to know. In fact, R1 will also generate this detailed content. R2 will also. R3 will also. Not just about this 3.3.3.3. For example, these two interfaces run OSPF. They also generate detailed information about these interfaces. After generating, the way is the same as R3. They are flapping each other. Then all learn the local. Count yourself. That is to say, all devices in the network will generate detailed content and will be synchronized with other devices. Then after synchronization is complete, it will bring a phenomenon. That is, each device has all the information about R1, R2, and R3. If R1 this generates a message. R1 passed to R2. R2 passed to R3. R3 has a message. Then R3 passes to R2. R2 passed to R1. If it is R2, here is a message. R2 passes to R1. Will also be passed to R3. So eventually it leads to a phenomenon. Is now in the entire network environment. All devices can actually get information about other devices. This has nothing to do with broadcasting. The broadcast we are talking about is more inclined to refer to a broadcast domain. At this stage we have not talked about VLAN. Everyone can understand that. They are on the same network segment. For example, there is now a switch. Multiple devices connected to it. They all belong to the 192.168.1.0 network segment. The switch now wants to send a broadcast data. Assuming a 24-bit mask. It can send 192.168.1.255. It's called broadcasting. In fact, broadcasting is also a flapping action performed by the switch. But the second and third floors are slightly different. You will often hear the word flapping in the future. The term is used in descriptions of different environments. Its meaning is slightly different. We'll talk about swapping in the next lesson. Also mentioned flapping. In fact, there is not much difference in essence. All except the interface that receives the data. Send another interface. This is called flapping. In fact, you can understand it as copying and sending a copy. But it's not broadcasting. All three devices can eventually get the information of all other devices. That is, R2 generates its own. R1 also generates its own. Eventually they all get information about every other device. Sync now. So now, all devices in the network will synchronize the same information. That is, everyone maintains the same information. The device is not in a hurry to calculate the route. When all the information is obtained, it probably knows that there are R1, R2, and R3 in the network now. No fourth device. Then look at what they post. Because there are many parameters in this detailed content, the device can draw a map based on this information. So each device will first synchronize all the information later. They go to calculate. It's like we learn. You have to listen to the teacher to finish all the bits and pieces of knowledge first, and then summarize. Distance vector routing protocols are relatively inferior to link state protocols. But EIGRP is an advanced distance vector routing protocol. So it is actually divided into two steps. For equipment, the first step is to synchronize link state information. Then go to calculate the route. This synchronization algorithm is called the OSPF algorithm. Let's talk about the characteristics of the distance vector routing protocol. You will learn about other link state protocols later. But they have the same characteristics. It passes the details of the device, contains overall topology information, and some connection status, cost information. It will spread. So each device can be based on the information. Build up the overall topology. Then after the build is complete, we can thus know the details of the routing in the entire network. The link state protocol is calculated using the OSPF algorithm. This is one of its characteristics. Then I want to ask you a few questions. How can we guarantee that this information will be synchronized? This is the first question. The second question is, what is the name of this detail? It's not the name, it's called details. In the network, anything professional, almost each has its own name. Then we will talk about several concepts of OSPF. For this detail, it has its own name, called LSA. After the device runs the OSPF protocol, some parameters it will produce. Of course, these parameters are not exhaustive. Let me say a few key ones at this stage. The first one is LSA. Its full name is Link State Information. It's what we call detail. Then we learn OSPF is to learn LSA. For OSPF, we will generate 6 LSAs in total. Actually, what we call LSA is very much. In our NA course, OSPF is probably taught in 1 class hour. There are about 10 class hours in the NP course. So it's actually quite complicated. But its principle is relatively simple. Now let's make some simple additions. For example, the device is now running OSPF. Then it is the same as EIGRP. It's all about declaring. There are 2 types of declaration. Also the same as EIGRP. First, declare the directly connected network segment of the device and neighbors. Lend it a neighbor. Secondly, announce some of the following network segments of the device itself. For example, R3 now declares the interface between itself and R2. Borrow a neighbor from R2. After R3 declared 3.3.3.3. This is the same as EIGRP. For example, in this, the IP address of the interface I declared. The mask of this interface I declared. The link type of this interface I declared. They are all the contents of the LSA. Include the current name of the device. Of course, the generator is not R3. We'll learn something later called router ID. This will be a router ID. That is to say, when I declare an interface, then all the information about this interface. In fact, it will be put into the LSA and then pass the. Here is an illustration of its simplicity. So you see now this is 3 devices. We assume that there are 3 LSAs stored on each device. If there are now 30 devices, do all devices have to be synced? In the case of a large number of devices, may these routers receive so many LSAs? Where do they put this data? Just like the device is now going to 3.3.3.3 is a route. The device now goes to 23.1.1.3 is also a route. These routes need to build a table for the convenience of viewing on your own device. Whether calculating or viewing, you must sum it up. Summarize to database. That is, on each device there is now another parameter. It is also critical. This thing is called LS database. We call it LSDB. This DB is the database. LSDB stands for Link State Database. Then it is where the LSA is stored. Just like the routing table where you store your routes. The routing table stores many routes. Then a lot of LSAs are stored in the link state database. This is a relationship between them. Is a containment relationship. Each device will form a database like this. Within the same area. LSDBs of all devices are consistent. We tend to say it's a barrel. Because everyone's buckets contain the same things. Including what equipment is installed. Generated information. Are consistent in the end. We also call maintaining an identical bucket. Let's take a look. It's actually very similar to the one I just drew. There are 3 devices. They all generate a lot of LSA. So now each device is flapping each other. Each device learns from other devices. It's called database. This database belongs to each device. That is, RA, RB, and RC each have one. And the databases in them are the same. It also looks like a barrel. For a device. It just needs to have all the information. Then it can be based on the OSPF algorithm. Calculate the number of shortest paths. This is what we call the shortest path. Each device counts as one. For example, this is RA. This node is A. Then it goes to RB or RC. Then it counts the number. Then go to route calculation. Only then can the routing table of the device be calculated. Relatively speaking, the principle is very complicated. At the NP stage, you will also learn how to draw this picture. Based on what we've shown. Neighbor appearance or LSA appearance. Invert this graph. So now we have to think about a question. LSAs generated by each device. How did it get into the LSDB of other devices? That is, R3 now has to give R2 pass. Then that's the problem. Like we do in real life. You want to tell others about yourself. Then you two have to get to know each other first. Equipment as well. The device now wants to pass information to other devices through OSPF. Then the two of them must first get to know each other in OSPF. Just like EIGRP. So you have to make sure. Before the device forwards the LSA, the two devices must first be aware of each other. They are going to establish a relationship with each other. Also called neighbor relationship in OSPF. It's just that there are two relationships. A neighbor. Adjacency. Whether neighbor or adjacency. Must ensure that the device can establish this relationship. They will be able to perform the next sync. If this relationship cannot be established, then they cannot be synchronized. So I will summarize the process of OSPF for you. The first step is to establish a relationship. The second step is to synchronize the LSA. After that, build LSDB. After building, the device will start to calculate the route through the SPF algorithm. So for OSPF, its process is relatively complicated. Devices need to establish a relationship with each other. Second, synchronize LSA. Build LSDB. The third step will be performed after the construction is completed. This is its process. You will focus on learning this in the NP stage. We will learn today how to build relationships. Actually, this corresponds to the three tables in OSPF. Neighbor table, database table, and routing table, corresponding to three steps. Let's read it together. In fact, most of the content we have already said. First, the neighbor table. There are some key parameters in the neighbor table, such as neighbor ID. This ID is the identity. Then the neighbor ID is the same. What it sees is not its own, because it is R1. Wait a minute, we must configure R1 to be 1.1.1.1. Everyone knows this. So 2.2.2.2 appearing here must be from other devices. Is R2. This is called the neighbor's router ID. Below this has a priority. Then this priority refers to the interface priority. That is, now R1 and R2 establish a neighbor. Then the OSPF relationship is also based on the interface. You will learn later that the division of regions is also based on interfaces. The establishment of the relationship is also based on the interface. We sometimes declare network segments. In fact, it is to declare the network segment where the interface is located. In fact, we are still declaring the interface. That is, now the two interfaces establish a relationship, because the interface is in the network segment. So we say it is to declare the network segment. You need to understand this concept. This priority refers to the interface priority. Look down. Here is a state called full DR. The interface priority depends on the priority of the peer. The neighbor of the device is 2.2.2.2. Neighbor's interface priority is 1. This full is the neighbor status. This DR is the interface status. It's all neighbors. Further down here is a dead time. For OSPF, there is also a hello packet. EIGRP also has hello packets. It's just that it is sent every 5 seconds. 15 seconds to declare death. OSPF sends once every 10 seconds. 40 seconds to declare death. So the 39 you see here is a countdown. Now the two devices send hello packets to each other. Send once every 10 seconds. As long as the device receives the hello packet sent by the peer, it will reset this to 40. Then start counting down until it reads 0. If the peer does not send a hello packet to it, then this neighbor is gone. Let's look down. Here is an address. This is the IP address of the neighbor interface. The device interface is 192.168.1.1. The neighbor interface is 192.168.1.2. And the last, interface. This is the interface used by the device to establish a neighbor with the other party locally. Only this is the device's own. The device uses its own local 10 and its neighbors. That is, the previous parameters are the parameters of the neighbors. Only the last one is the parameter of the device itself. Let's look at the OSPF database next. For the database, there are all kinds of LSAs in it. We won't talk about this stuff now, so everyone simply understands the concept. Further down is the routing table. We are actually very familiar with the routing table. First of all, O means that the above is OSPF. Sometimes you may see OE2 here. OE2 means this is an external route. That is, the redistribution comes in. Remember redistribution? The left side of this device is EIGRP. On the right is OSPF. Then I wanted to learn the routes learned by EIGRP here. I'll redistribute it in. Called routing. Also known as route redistribution. If it is like this. If there is a 1.1.1.1 route here, a 1.1.1.1 route will appear in the routing table. OE2 is a representation in Cisco. Let's talk about the last. Is some theory of OSPF. Administrative distance. The external is the redistribution I just mentioned. Then you will find, in Cisco, the overall management distance inside and outside OSPF is repeated. Then if we do heavy division in the future. In fact, in some cases it will cause problems. You will also address these issues in the future. Now let's not talk about this knowledge. Because you can't learn it. In the future. You must first learn the division. Then learn this thing. Let's talk about the latter. Updated multicast address. Remember what the multicast address of EIGRP is? It is also 224.0.0.10. The multicast address of RIP is 224.0.0.9. OSPF is special. It has two multicast addresses. One is 224.0.0.5. One is 224.0.0.6. Wait until we finish talking about the state of the interface. Talk about these two multicast addresses. But you need to know. OSPF uses 0.5 and 0.6. The above part is actually some boring theory. Then we will start to look at the part of the message. OSPF has 5 types of packets. Respectively, hello, DD, LSR, LSU, and LSAC. The first is the hello packet. It is a message to keep alive each other. Further down here are some summaries of what we sent. For example, I send you a list. We'll talk about this relationship in a minute. Further down this is a request. Then update. The last one is to confirm. This is the 5 packets of OSPF. There is a saying in OSPF. OSPF has 5 messages and 7 states. This is what everyone must remember. Before we talk about the message, first you have to know where OSPF works. That is, data encapsulation. Where is this message encapsulated? It is encapsulated on top of the IP layer. Everyone can see. Preceded by an IP header. Behind the IP header is the packet of OSPF protocol. Then in IPv4. I have also said, there is a thing called the protocol number. When the agreement number refers to 89. That means the upper layer is the OSPF protocol. This is a guide for the 3rd floor to the 4th floor. Sometimes you will hear a sentence. OSPF is a routing protocol that works on top of the network layer. That's what I mean. It's above 3 floors. That is, above the network layer. So what we just saw. What does the updated multicast address mean? Let's go with this picture. When we talked about IP before, we told you there are some important parameters in the 3 layers. E.G. Source IP and destination IP. The source IP is. Now which address is the source of this message encapsulated? Generally speaking, this is the IP of the outbound interface that sends the message. For OSPF, there are only 2 destination IPs. One is 224.0.0.5. One is 224.0.0.6. It uses these 2 addresses for overall update and learning. That is, this address will be filled in the destination address of the layer 3 IP. This message is sent to the multicast address. Then other devices in the entire network will listen to this address. Let me give an example to explain the meaning of monitoring. If a device sends this data to point 5, another device monitors point 5. Then it can know the information sent by another device. We sometimes say, send information to other devices. But it's not like sending it directly. Send it here. It goes to listen. That's what it learns. Then it learns. This is called the OSPF updated multicast address. Then I will also emphasize a knowledge to you. For OSPF packets, it refers to the OSPF message transmitted in a broadcast domain. It has a feature. Its TTL is equal to 1. When encapsulating data at 3 layers, there is a time to live in IPv4. After the message is sent out, the number of times that can be forwarded by the 3 layers. If R3 sends a message now, TTL is equal to 1. After receiving R2, its local value will be reduced by 1. Subtracting 1 equals 0. Packets are no longer forwarded. It is equivalent to the end of its life. So actually TTL is equal to 1. This means that it can only be transmitted in one network segment. For the device below, it's impossible to retweet it once. Then the process it sends out is called flapping. The generator of the data is R3. Sent by other devices. Is exactly the same message as. Then when the data is being sent, it's not called forwarding. Called flapping. TTL is the time to live of OSPF overall packets. So it can only be delivered under one broadcast domain. Current stage. You can temporarily understand the broadcast domain as the same network segment. Now for us, each router interface is a broadcast domain. So broadcast messages can be sent so far. And OSPF is also because TTL is equal to 1. It's called hop-by-hop transfer. Hop-by-hop transfer means that devices must transfer one by one. It has no way to cross the traditional. These are some basic encapsulation forms of OSPF we are talking about. Then let's discuss a few parameters. After finishing speaking, let's talk about 5 messages and 7 states. And after speaking, check the configuration according to the parameters. Okay. Let's start with several parameters in OSPF configuration. The first is the process ID. OSPF has a process ID. It is used by this device to identify the OSPF process. Suppose there are a lot of processes running on the device now. Now there are many apps on the device. Actually, every application is an RID. That is, router ID. Now you will see. There are many processes on the device. The data I am generating in the browser now all belong to this process to maintain and calculate. OSPF is the same. You enable OSPF on the device. You can understand it as software on the router. This software is called OSPF. Then this software has to occupy a process in the device. It needs to call some hardware performance inside for calculation. Then there will be a special space range for maintaining internal data. We call it a process. Then under this process, information about all your interactions, configuration you made, the announcement you made, will be owned by the process. It will help you maintain and calculate. That's what I mean. In addition, OSPF processes can open multiple, but at the moment only one, between different processes. You can declare different content. I give a simple example. For example, this is a device. I can open OSPF 100 on this device. Open another OSPF 200. Then they are isolated from each other. There is a network segment on this device. Is 1.1.1.1. Here is a 2.2.2.2. If you declare 2.2.2.2 in process 200. 1.1.1.1 declared in process 100. They do not affect each other. They are completely separate relationships. Suppose there is another device in the future. It establishes a relationship with this interface. So now declare. It is configured in process 100. You must have established a relationship with it in process 100. Then this device. You can learn the 1.1.1.1 network segment you are announcing now. But it cannot learn the network segment 2.2.2.2 you announced. Because the processes are isolated. You opened a different process ID. It is equivalent to multiple OSPF. OSPF opens two process IDs. This is two OSPF. The contents of each other are non-overlapping. Later you will learn. There may be many ways to connect devices. Then you will encounter all kinds of problems. You must never open a process on the device 10. Made some builds with it in. Then opened another 20. Made some builds with it in. Opened a 30. Made some builds with it in. Finally, it was found that the entire network was disconnected. It doesn't use much. So just let everyone know. And the process ID is locally valid. Locally valid is if OSPF is running between two devices. The process ID can be different between them. They are also able to establish a normal relationship. This is called locally effective. This is the first parameter. Further down there are other parameters. The next parameter is the router ID. How is it identified? Let's go back to this picture. We just wrote here that the generator of the message. I am in R3 if I make some announcements. Then the device will generate information. A device generates information to tell other devices. So we will fill in the router ID of this device here. Tell other devices that this information was generated by it. So in the information generated by each device will carry its own router ID. The router ID cannot be repeated. For example, now, between R1, R2, and R3, each device generates some link state information. They are not repeatable. It's like our graduation thesis. Everyone can't write the same content. The same is true for routers. Now the exchange is LSA. Then the LSA must indicate who originated it. I give an example. The router ID of R1 is A. The router ID of R3 is also A. R1 is now on the 12.1.1.0 network segment. R3 is on the 23.1.1.0 network segment. That is, now A has generated two messages. R1 belongs to this network segment. R3 also belongs to this network segment. Then please note, it generates this information based on the interface. That is, this interface will be this network segment. It will be this network segment. This is outrageous. There is no way for our information to be synchronized and calculated, because information can be confusing. So, under the same region, the router ID must never be repeated. But in the future you will learn OSPF multi-area. Then under multi-region. That is, under different regions. Sometimes the router ID can be repeated. We just talked about LSDB. I said all equipment will maintain a bucket. This bucket contains information about all devices. We will learn in the future. OSPF is based on area to synchronize LSDB. For example, these devices now belong to a region. Belongs to area 0. Then there are some devices that belong to another zone. Belongs to area 1. Certainly. There will be a device in the middle. So here are the different devices. Suppose the device is called A. In fact, this device can also be called A. Then if the two devices, no other data interaction will be performed. They can. But sometimes there is a problem. When I introduce a root on this device, originally, they would maintain a. In fact, the contents of the calculations do not interfere with each other. The two of them ultimately do not need synchronous routing. How to perform data forwarding in the end? There will be a default route here. After this, you will learn it at the NP stage. But I tell you, there will be problems when this thing is repeated. In this case it can actually be repeated. But if I'm on this device, introduced an external route, it becomes another character. You will learn ASBR later. It is equivalent to an externally introduced router. If it introduces a message, then it will generate a link state message at this time. Identifies that this is generated by device A. Then the message it generates at this time will span the region to other regions. Routers also receive information from other areas. Then it won't work at this time. When it is received, just tell other devices. It doesn't import at all. It doesn't have this route at all. Then this message will come back. It won't come back in this area. Instead, it will be delivered within this area. It will go haywire. I say now that you may sound a little confused. But what I want to say is, it is not absolute whether it repeats. In the same area, it is absolutely impossible to repeat. It can be repeated or not repeated in different regions.